Welcome in. All right, so another video with regards to these elastic collisions. Now, I am going to take a look at two extremely special cases, and I'm going to derive these two particular formulas for you if you wanted to know what the velocities are, what the final velocities are for one-dimensional collisions. All right, so this is not in 2 dimensions or in 3 dimensions. They're just two objects that are going to be colliding, okay, to each other. And that's what we want to be able to do in this video. So I'll try to show you this. I don't recommend that you memorize these equations, although probably I would have if I was in grade 12 and doing this all over again. But it is nice to know where they come along with, and that is actually from these two. Now, the special cases that I'm going to highlight in here are going to be these two special cases. So once you have these two equations, then it's not very difficult to show that if you take and you assume that one of the objects is stationary, it doesn't really matter which one, all right? So in this case, I'm assuming that VI2, so this one is stationary right there. So if you set this to 0, of course, and this term will fall out, and then these are going to be your final velocities or final speeds that you have. So that's not anything extraordinary. But it gives you a very nice and simple equation for that special case when one of the objects is actually 0, meaning its speed. Now, the second special case that you have is this one, when one object is just simply huge in comparison to the other object. So let's say M2 is much, much heavier than your object M1. And in this case, because of that particular object, we're also going to be assuming that this, meaning your heavy object is stationary. So it's literally like, hitting a truck, that is stationary. Let's say you throw a tennis ball at it, that the tennis ball is just going to bounce back and nothing's going to happen to the truck. So you can see that these equations, which you have right here, if this one, is much heavier than this one, or vice versa, it doesn't matter, then these two equations nicely lead you into this. So I'm going to come back to that, all right? So we'll come back and show this, right afterwards. But the first thing that I'll do is I want to show you how you can derive these two particular formulas for this, all right? So it's going to be a little bit annoying, but hopefully, speed up some of the components, and then I'll just tell you what to do, all right? So here we go. We want to get this equation, let's say, first, and then the same thing follows for the second one. So I'm going to steal this out. I'm going to take this equation, and I'm going to collect my two M1 masses. I'm going to bring them on one side, and I'm going to take the M2, and I'm going to bring that on the other side. All right, so that's the first thing that I'll do. All right, and I'll do that in fast forward fashion. And we're back. All right, so that's the first item that we have. All right, so I just took it, rearranged it, and now I factored out the M1. All right, now you'll see why that will be necessary soon. Now, the next thing that I'll do is this. So I'm going to take the left-hand side and the right-hand side, and I'm going to do the same thing, I'm going to bring the M1s together. So I'm going to bring this over on this side, and I'm going to shift this over on the other side. Notice that I can get rid of this half by multiplying by 2 on both sides, right there. So that's going to get rid of that. All right, so that's the next thing that I'm going to do. And then you'll notice that something will happen. So I'm going to pause right here because I just want to show you what's next. So notice that, now they look very similar in here, except the one right here, which is coming from the conservation of kinetic energy, has the squares. So I want to bring you back now to math because notice that you have a difference and then you have these squares. So this is a difference of squares. And the same thing happens here. You have a difference of squares right here. So I'm going to factor this out by the difference of squares. All right, so I and did the factoring out, and then I highlighted, okay, that M1 that you see there, and then the first term on the left, and then on the right. And what I want you to now notice that this is exactly what we had from the conservation of momentum right here. So notice these are identical, right? So this term right here, so that factor actually and this factor, they're identical, and so are these. Now, these two are equal to each other. So what I'm going to do now is I'm going to do the following. I'm going to take all of this. I'm going to now divide both sides by this right here. So I'm going to just duplicate it. I'm going to divide both sides by this. So really what I'm doing is that. And now, because of the fact that this is just equal to that, right? Which means that I can simply, instead of having this, I can replace it. So I'm going to just shift it out of the way for the moment. I can just replace it by that because they are equal to each other. And if I do that, of course, this whole thing cancels and this whole thing cancels. Now, we are assuming, so within here, that we have the V2F minus V2I. Okay, they're not equal to each other because it would give us 0 in the denominator. So we have to be careful, right? So this minus this cannot be equal to 0 overall. But that cancellation will happen. So I'm going to remove this whole thing right there. And from this, so notice what you have is you just have this right here. And that is equal to this right here. I'm going to do that. And so from here, I'm going to now isolate. So I'm going to isolate for this. And that's going to give me V2F is equal to, so this minus the V2I. Okay, so right above there. So I just shifted that over on the other side, but I just wrote it from left to right. Now, once I have that, all right, so once I have this, remember that our goal is to try to show these two equations. That's what we want to be able to show. I'll show one of them because the process is exactly the same for the other. So why did I isolate for V2F? Because of the fact that what I want to do is I want to, so take all of this right here. So I'm going back to my law of conservation of momentum for the two objects. And I'm going to now take V2F right here. And I'm going to substitute it right in there. All right. I'll do that in fast forward fashion. So now once the substitution and the distribution of the M2, now I'm going to collect, okay, so everything that I need. So let me just now collect all the different like terms and then factor things out as necessary, all right? So let's take a look and see what happens. So now rearranging and then just collecting. So the last thing that remains is we're going to divide, okay, so everything by this right here. And we're going to be able to isolate for that V1F. All right, so this will cancel. And of course, we're going to do that on the right-hand side as well. So we would have had that right here, and we would have had that right here. And what will happen is you're going to get exactly the formula that you wanted. So that particular formula, so which is this one, so I'll duplicate it, okay, bring it back down. And now you have written out your final speed or velocity, okay, with regards, I'll just shift this out in the back here. All right, let's shift this out as well. So this is what we would have, okay? So overall, we have just now shown the whole entire derivation of that first formula right here. So notice this, 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 and here are your factors right in front. Now, you can show this exactly in the same fashion, all right? So you can do that, except, so if you were coming back to over here, so instead of isolating for V2F, which is what we substituted back in here, you would have just substituted for V1F. So if you do this, and I encourage you to do that, so if you take this, isolate it, and then substitute it back in, except you would be substituting into here, you would be able to massage this and obtain the second formula. Now, again, if you're looking at this, this only works for elastic collisions in one dimension. And yes, you know, so these equations are really nice because now if you have an example, then you can just apply the formula itself. You don't actually have to deal with these two. But me personally, so as someone who is being this and instructing and lecturing, I don't encourage students, you know, to necessarily memorize these, but actually know where they're coming from. And the ultimate trick is that indeed it's coming from the elastic collision. So that's how we're able to obtain this. Now, coming back, okay, we've explained, because now once we have these two formulas, this one is very easy to explain. So the special case, when you're assuming that one of the objects is stationary. Because once you have this formula, well, if one of them is stationary, the term just falls off. And then you can find out what your final speeds are. And again, please remember that if you are talking about something positive and negative, don't forget to substitute a negative sign if it's moving in the opposite direction so that you do get the correct sign on this because the vector symbol is dropped. Okay. Now, what about this, right? So within here, where exactly did that come from? So let me take this and copy it. And I just want to show you, so what we are now saying for the second special case is the following. So we're stating that now M2 is much, much bigger than M1. Okay, so that's that. And we are assuming that that object has its speed initially at 0. So basically it's a huge, monstrous object. You know, you can imagine anything that's really, really big in comparison to the others. And notice what happens. It states here that in that case, these copy, I'm going to bring it back down here and paste it. What it says is that the object that is really large and it's stationary pretty much remains stationary. Again, remember that if you have a huge truck and you throw a tennis ball at it, it's just going to bounce off, right? Or anything that is much, much bigger and larger. So now, where did that come from? Well, because if you look at this formula and you know that this is much larger than this, then what happens is that that first term, so this 2m1 divided by m1 plus m2, okay? Think about, let's say that, you know, let's say m1 is equal to 1. Now, I'm just making this up, but I'm just trying to show you that when something is really, really big in comparison, so let's say, you know, this was like 10,000. If you substitute that in here, well, what is this going to give you? It's going to give you 2 divided by, you know, 1 plus, you know, 10,000. So really, okay, if you're looking at this, this basically is approximately 0. So that's why, you know, that is going to just fall off. And the same thing happens right here. This is going to fall off as well because you have M2, okay, divided by, so my apologies, so I have to be careful when I say fall off and what I mean by that. So M2 minus M1 divided by M1 plus M2. Okay, so within here again, if you take something like this and you substitute it back in here, so notice you're going to get something which is really large, okay, minus something which is really tiny, and then something which is really tiny plus something which is really, really large. And really, this, okay, is approximately equal to 1. Right? Because if you take this and divide it by that, it basically is going to be equal to 1. And that's what I mean. So this now falls off as well. So this is equal to 1. this one is equal to 0, and therefore your final speed is indeed, okay, going to be approximately equal to 0 because it's equal to its initial speed, and we were assuming that that initial speed was equal to 0. So that's that special case. Again, a very large object that's not moving. If you bounce into it, it's not going to move. It's just going to kind of stay there stationary. And on the other side, if you do this and you plug this right back into here, and I encourage you to convince yourself, that smaller object is basically going to be bouncing back with the same speed that it was thrown at it. Again, these are elastic collisions. So we don't have any dampening or anything. So basically, it just returns with the same speed that you threw the tennis ball at the big object, except in the opposite direction, because it just bounces back. And if you substitute those numbers into here and into here, this is exactly what you're going to see. Okay, so this, of course, because of that, falls off to 0. So that would be irrelevant. And then this right here, right? So you have a very tiny object, and then you have a very huge object. So that's where the minus will come from. And then it will be divided by just by the huge object's mass. And that will be basically just in the reverse direction. So there you have it. So it's a little bit of a case of some fun math and derivations for elastic collisions with some special cases. So you can use these to your advantage, and I hope that you understood the derivation for this in 1D. All right, okay, we'll get into some examples later on in future videos. Thanks for watching. Bye, everybody.